Okay, so some people may ask, what exactly is mathematics? There are so many definitions, yes, that some maths teachers try to use to describe what exactly mathematics is. But if you take a closer look into those definitions, they have a common way of explaining. What do I mean by that? Look, when many people hear the word mathematics, you know what they quickly think about? They think about symbols like numbers. Some they think of letters like X and Y. Some they think of crazy symbols like the integral symbol or plus or times. Some they think of Greek letters, etc. But mathematics actually begins, you see, if I push this book, right? Or if I push this marker, a lot of things have happened here. There are so many ways of describing this situation. But the best way of describing what is happening here is to use mathematics. So mathematics is a precise way of explaining everything that happens around us. It's a precise way of describing the reality of the things that we experience in everyday experiences. For instance, I pushed this book with a particular force, right? But that same force that I pushed the book is the same force that I've also used to push this marker. Mathematicians now, they tend to, in real life, so many things happen. There are so many things that happens around us. Can be in relationships, can be how markets behave in economics, can be in electrical engineering, how electrons behave, can be in civil engineering, how a particular bridge has to be constructed. So all these phenomena, to describe them precisely, mathematicians, they ended up using mathematics. But what do we mean? What is now maths? So mathematicians, they take the symbols, right? What do I mean by symbols? Trust me, like I said, many people, when they hear the word mathematics, they think of numbers. Yes, numbers like 1, 2, 3, 4, all the way to 9 are some of the symbols that we use in mathematics to represent quantity of something, right? But what if you are not yet so sure with quantity? Mathematicians, they tend to use the Greek letters. They tend to use the Latin letters. The Latin letters, all of us, we are familiar. Those things are introduced at an elementary level, like grade 1, grade 2, grade 3. Things like A, B, C, D, E, blah, 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 up to W, X, Y, Z. So mathematicians, they also tend to borrow these Greek letters, not Greek letters, the Latin letters, these are Latin letters, to represent an unknown quantity, right? For instance, I can say, I've got a certain amount of money in my pocket. That certain amount of money, I can represent it and say, I've got X dollars in my pocket. Or I've got Z cents in my wallet. Or my father has A dogs. A represents the number of dogs, etc. But because there are a lot of things that needs to be named in mathematics, we see that, okay, using these Latin letters, it's not enough. So we then borrowed from one of the ancient languages. What do I mean by ancient? Because things like Latin, they were born out of the Greek letters. So Greek is the ancestor language. If you look at going to the Bible, see like guys like Jesus, people who were back then in old days, like around 200 BC, they used to use Greek. It's still used even nowadays. So today, let me explain more about this Greek. I think so as to make, because majority of the people, they are familiar with numbers. Majority of the people, they are familiar with the Latin letters. But some people, they feel like, mathematics is difficult because of this Greek letter. Imagine if you see something written like, okay, let's say if I say the gamma of JD, right? And then I'll say is equivalent to, can I say the gamma of JD? Okay, let's say maybe the beta of JD is equivalent to the gamma of J times the gamma of D, right, divided by the gamma of J plus D. Immediately, when you see a statement like this, your adrenaline starts to rush throughout your body because you feel like, oh, this is complicated. Why is it complicated? Maybe because you don't even know how to read. So you can't know the meaning behind. If you can't even know how to read these symbols, it's not about symbols. Symbols, they are just attached to something that you already know that is happening in real life. Can be in social life, can be economics or whatsoever, like I said. So what is this? Like I said, this is beta. What is this? Like I said, this is gamma. So as you are learning mathematics, Greek letters are introduced like at a low level. Like personally for me, when I was studying mathematics, I started to see theta when I was around in Form 1, Form 2. And as I advanced to Form 5, Form 6, I started to see other Greek letters like alpha and beta. As I move on further, I started to see other letters. They were slowly being introduced in different modules. But I told myself, no. Let me try to start them so that reading mathematics can be easy. Because I realized that mathematics, like I said, it's only these numbers, 1 to 9, Latin letters, as well as those Greek letters that I feel like I must explain in detail for you guys to know. And then maybe the rest are also connectors like equal sign, plus, etc. But let's talk about Greek letters. So the first letter is alpha. So what I'm going to do here, I'm going to show you the capital letter for each and every Greek letter and the lowercase. And then after the lowercase, I'm also going to show you how to pronounce it at the same time, right? So the first one, like I said, this is alpha. So the interesting part, some of the Greek letters, especially the capital letters, they look analogously to those ones of Latin. For example, if you look at A, this is the same A for Latin, but this is also the capital letter for A in Greek. But the small letters, they are the ones that we tend to use in mathematics. And if you look at them, they are very crazy. Like this is how we write alpha, right, as a small letter. So this is written as alpha, right? And then after that, we've got beta. So it's almost like capital letter B, right? But if you want to write the small letter, it's this one. So you see in mathematics, we pretend we love this small letter. We love these small letters, unlike the big letters. So this one you read as beta, right? Then we also have gamma. So this is capital letter gamma, and this is the small letter gamma. So we read this one as gamma, right? Then after gamma, we've got delta. So this is capital letter delta. It's more like a triangle, or you can write it like this. So this is delta, right? So where do we see beta? Like you see, look at this beta function, which is also connected with the gamma function. A very, very interesting result. I will explain in detail in other lessons what exactly is a beta function, what exactly is a gamma function, etc. But we tend to use these symbols even in physics, like alpha, we tend to use in physics, especially in civil engineering or electrical engineering, beta, gamma, and delta. Normally delta plays a fundamental role, especially in calculus for changes, etc. Then after delta, we've got epsilon, right? You can see E, like a normal E from Latin, but the way we write it now in Greek, it's like this. So you read this as epsilon, right? Epsilon. So after epsilon, we have got zeta. So you write it as a capital letter Z, but the small letter is what matters the most, like I said. So you write it like this. So that's the small letter for zeta. So we pronounce this as zeta, right? So if those ones who did a bit of Riemann hypothesis, we always talk about the zeta function. It's quite interesting there. So we normally represent the zeta function with this symbol. Quite interesting. After the zeta, we have what is called eta. So we've got capital letter H like this, but the small letter is a crazy N like this. We pronounce this as eta, right? So after eta, we have what is called the theta. So theta is written like this. You may find out that if you are doing mathematics, theta is introduced at a lower level. Like when you start doing geometry. Remember, there's Euclidean geometry. There's a lot of things to learn in Euclidean geometry as far as the axioms of angles are concerned. So in Euclidean geometry, you need to understand what exactly are straight lines, parallel lines, angles in a straight line, vertical opposite angles, angles in a circle, etc. So you may find that we tend to borrow this this Greek letter like theta to represent an unknown angle. We read this as theta, like this. That's how we read this, this Greek letter theta. So this is small letter theta and caps theta. So after theta, we have iota. So this iota is iota like this, right? And then after iota, we've got kappa. Kappa is used a lot. Kappa is used a lot, especially in Riemannian geometry, whereby kappa is used for curvature. If you are looking at the curvature of a curve, imagine if something is moving in a particular space. So we want to see the curvature. We normally use kappa to denote the curvature. After kappa, we write this as kappa like this. Right? That's kappa for you. Then after kappa, we have what is called a lambda. I've used the lambda a lot when I was studying mathematics. If you're doing linear algebra, let's say you analyze a particular system and you're trying to solve the variables that have been changed in a particular system, you come up with what are called eigenvalues. Mathematicians, they love to denote these eigenvalues with this Greek letter lambda. This is capital letter lambda, small letter lambda is like this. We normally denote those eigenvalues with the letter lambda. Remember, those eigenvalues, they help us to understand the system better in terms of its stability or whatsoever. So once we have the eigenvalues, remember, that's when we go further and calculate the eigenvectors. So lambda, this is how we write it. It's lambda. Like this. That's how we read this letter. So after lambda, we have what is called mu. So capital letter M, like what we do in Latin. Those ones who did A, B, C, D very well, they know this letter M. But in Greek, we write it a bit stylish. Mu. Mu. So you read this as mu. So this is the mu. It's a U which is a bit stylish. That's our mu there. So that's our mu. After mu, we've got what is called the nu. So when you are writing nu is just a little bit tricky. So you write this as nu. So after nu, we have what is called xi. So it's a bit funny. It seems like you're writing an E, but not actually an E. So this is capital letter for xi. If you write the small letter for xi, it's like this. So this is xi. Right? And then after this one, we have what is called Omicron. So it's just O, just like this. We call this Omicron. Okay? After Omicron, then we go to pi. Right? So pi is like this. You know, this number, many students, they have encountered pi because pi is introduced as low as from grade 5, grade 6. Pi is introduced. What exactly is pi? Pi is a Greek letter, like I'm saying, but it was taken by mathematicians to represent something so beautiful. Mathematicians discovered something quite interesting. They've realized that if you take the circumference of this circle, right? If you take the circumference of this circle, right, and divide by its diameter, by the length of its diameter, there's a number that we get, no matter how big the circumference is. It might be the circumference of my pupil or the circumference of my iris. But if I take the circumference of my iris and divide by the diameter of that iris, the answer that I get is 3,142 something. It's called an irrational number. If you have explored some of my videos on number theory, go there so that you understand what exactly irrational numbers are. So we get that irrational number where mathematicians, they decide and say, okay, what can we do? Since this number is so unique because of its beautiful properties, like I said, regardless of how the circle is, if you take the circumference of a circle and divide by its diameter, you get pi, right? So who is pi? Pi is a number It's a symbol that represents the answer that we get when we take the circumference of a circle and divide by its diameter. It's written like this in small letter pi, right? Some people, when they hear the word pi, they think of that one that we normally eat. There is no problem of attaching this to that one that we eat. That's what mathematicians also do, like attaching some things to some things. But anyway, so after pi, we have got what we call rho. So capital letter P, or you can write it like this. You read this as rho, right? Rho. Rho is used in so many areas in mathematics. One of the areas that it is used probably in civil engineering, let's say maybe you are trying to construct a boat. We want to know the density of that boat because by the end of the day it's going to be in water, right? So to calculate the density, so for density, like I said, mathematicians, they love to attach something. They want to see, is this thing going to float or not float in water? So that floatness is normally denoted by letter P for density, right? So we know that density is mass over volume. So rho sometimes is mass over volume. That's where they love to use the letter rho. That's where it is borrowed. So from rho, we've got sigma, right? So when it comes to sigma, sigma is so beautiful. It's used in so many areas. I can't tell you which area, but so many of them, whether you're in real analysis, whether you are in calculus, whether you are in statistics. Look, statisticians, they normally use sigma when they want to represent the sum of. So the word sum, this one, they use it to represent sum of, but it's basically a capital letter for sigma. The small letter for sigma is this one. Sigma looks like delta, but there's a great difference between sigma and delta. Look, the way I wrote my delta and the way I wrote my sigma, just write 0 and 2 in this way. So this is sigma. Normally sigma used for standard deviation, but if you look at this one, it's normally used for sum of. For example, if you want to calculate the mean of something, you say mean, which is normally denoted by x bar, is equivalent to the sum of all the values divided by the number of values. They call it the mean. This is very important, especially in statistics. Remember, statistics is the science of decision making in the face of uncertainty. So if you want to make a decision, obviously gather the data. Once you have the data, figure out the averages. Those averages can help you to make a decision. And sum of, we borrow from this Greek letter called sigma, means sum of somewhere, somehow, sigma. Okay, so after sigma, we have what is called tau. Capital letter T, or a stylish small letter t like this. We read this as tau. Who is tau? Like I said, it's just a Greek letter, but mathematicians, they, like, let's say you are doing Riemannian geometry. We normally use for tau to calculate the torsion, how a particular object that is traveling in space and time is twisting around. So torsion, mainly for tau, goes sometimes hand in hand with kappa, where kappa is used to calculate the curvature of a particular curve. So we read this as tau. Okay? So after tau, we've got the one that is written like capital letter Y, but the small letter is funny. It's like this. If you look at it, it looks like it's new, but there's a difference. For new, it's like you do this, right? It's almost like a V. This one also looks like a V, but look at how it's curved underneath. It's called Upsilon. Listen, the name, Upsilon. Sounds like Epsilon. These guys, they mean Upsilon and Epsilon and Upsilon. They mean differently. So you need to be very careful there. So after Upsilon, what do we have? What is the next thing that we have after Upsilon? That's when we go to phi. So phi is something like this. Throughout my studies for mathematics, where do I normally use phi? Oh, I used to use phi. Imagine if you are trying to solve a particular dynamical system. You may come up with solutions of that particular dynamical systems. Okay, let's say maybe you get x1, x2, x3, blah, 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 blah. If you take these solutions, you can form a particular matrix. And that particular matrix, you can call it phi, where phi is a fundamental matrix formed by the solutions of a given dynamical systems. I tend to use phi to calculate that fundamental matrix. The small letter for phi is this one. You pronounce it as phi in this order. So that's our phi. Then after phi, we have another letter which is quite beautiful. Statisticians, they use it. It's called the chi. There's what is called the chi square in statistics. Statisticians, they know what I'm talking about here. So it's called the chi, although it's a stylish x that you have to write in that particular case. Then after chi, we have psi. The symbol for psi, it's a bit scary. If you check around, they normally use even psi in other secret areas. I also use psi when I also play around with the conjugate solution of the fundamental matrix. So I also use psi in such cases. So you read this as psi, psi, right? After psi, we then go to the last one. The last one is called omega. So it's written like this. To students who are doing electrical engineering, they normally use this one for ohms when they are calculating the resistance in a wire, etc. So this is omega. So this is more small letter for omega. I know these words back then when I was 2 years. My mother is a prayer warrior. You know, when she's praying, she always say, "Hey, the God of Alpha and Omega, please bless my son to be a mathematician." So she always talk about these Alpha and Omega things. That's why I say, okay, the first and the last. I think that's where it was derived. So yes, these are all the Greek letters that we have. So what do you need to know? You need to know these Greek letters, especially if you want to study more mathematics. It will help you to know how to read mathematics. So besides the Greek letters, you also need to know the normal numbers, like 1 to 9. But remember, numbers were then extended. It's not just from 1 to 9. Numbers were extended into other forms. Numbers started with natural numbers. Mathematicians later realized that, oh, they are integers. And then they later realized that, oh, they are rational numbers, irrational numbers, complex numbers. So those ones who are interested in understanding all the types of numbers, check out for my video, Number Theory, where we break down the basics of number theory, understanding prime numbers, factors, multiples, and what really makes numbers work, etc. Then we also have letters like A, B, C, D, E, F, G, all the way to Z. Like I said, we also use those Latin letters to represent things that we don't know. I always explore these letters when we are doing the module for algebra. When we dive into algebra, we try to solve equations, working with expressions, and try to master patterns. But we tend to use these symbols to represent that we don't know. And sometimes Greek letters, especially when it comes to Euclidean geometry and Riemannian geometry, we tend to use Greek letters the most when we explore geometry. Remember, geometry is about understanding space and structure, studying lines, angles, circles, and shapes, etc. And then we also need to know the connectors, right? What do I mean by the connectors? Things like plus, minus, terms, divided, the integral of, the derivative of, right? Brackets, the meaning of brackets, and union. For each, there exists, right? For each, etc. All these other connectors, we also need to know them so that we'll be able to create a story within this line. For example, I can also create my story and then say, beta plus 3 beta, right, is less than 2 gamma, right? With that kind of a statement, we have combined the Greek letters, the connectors for the symbols, and we have created something. But what is the main objective by the end of the day? Like I said, this what is by the end of the day builds mathematics. But with what objective? With an objective of trying to describe reality in a precise way. So that's where mathematics begins. Can I describe this thing? Can I describe this situation precisely? That's where mathematics comes into play. That's why I always say mathematics is the language of everything, the language of the universe. This is where the universe is encoded